I want to address this issue that came up near the end of the last video, which is this idea of how to compute a probability of this or that happening, right? So event A or event B. We saw a couple examples where it worked out very nicely in the last video, and I mentioned that it's not always going to work out that nicely, so we need to be a little more careful. And so I want to illustrate this by way of an example. All right, so let's consider the following scenario. We are going to roll a fair six-sided die. And we are going to flip a fair coin. All right, so we've got the die, which has 6 possible outcomes, and we have the coin, which has 2 possible outcomes, heads or tails. All right, so I just want us to consider this for a second, right? You roll the die, you flip the coin, and for instance, if the die shows a 4 and the coin shows tails, then that event would be 4t, right? That would be 4 on the die and tails on the coin. If it showed a 1 on the die and heads on the coin, that event would be 1h. All right? So all the different events in this probability experiment would look like die outcome and a coin outcome. All right, so let's look at our sample space. I haven't actually given us a problem yet, right? I'm really just sort of ambling through this example. I just want us to think about some things before I actually formally state a problem that I want us to solve. All right, so these are things that you should be comfortable with, which is why I'm sort of approaching it this way. If we look at the sample space for this experiment, remember this is the set of all possible outcomes. Well, the first thing I want to do is ask a question. How many are there in this set of all outcomes? Right, so what's the number of events possible? And here we want to go back to our combinatorics work because we're trying to count something, right? Whenever you ask about the number of something, you're trying to count it. And so what we want to look at here is we want to view any event is really like 2 decisions, right? The die has to be rolled and the coin has to be flipped. Right? So you can view this like 2 decisions that need to be made. The die decision can be made in any one of 6 ways because there are 6 sides on that die. And the coin decision can be made in 2 ways because it has 2 sides. Fundamental counting principle says to multiply those 2 together. So there are 12 total events in this sample space. I'm only doing this because I want to make sure that if we list out all the events, we should come out with exactly 12 of them if we counted them, right? So this is like a way of checking your work and making sure that you're on the right track. All right, so let's just go ahead and list all the possible events. And I want to be systematic about this. So maybe what I'll do is, let's say you've got heads on the coin, and tails on the coin is your other option. Well, all the different ways that this can be done, you could have, the die needs to be rolled as well. So you could have a 1 on the die, or a 2, or a 3, or a 4, or a 5, or a 6, right? And all of these are going to have, right, heads is one option for all of these. Or you could have the exact same outcomes on the die, but paired up with tails instead, right? If you flip the coin and you got tails for any of these, then these would be your other options. Okay? If we count them, there are 6 here, 6 here, 6 and 6 together gives us the 12 events that we knew we were supposed to have. All right, so I think we've done this correctly. Let me list it out in set notation, just so we have the sample space written out. All right, so our sample space for this experiment could be written out like this. Curly braces, 1H, 2H, 3H, and so on. Whoops. And the same thing but with tails. 1T, 2T. All right, so that's our sample space. It contains the 12 events that are possible. Now, we can ask a lot of questions here. I'm going to ask the one that addresses this question I had at the very beginning about how we actually compute the probability of A or B occurring. All right, so let's ask a question here. What is the probability of heads or even? And what this means is that you flip the coin and you roll the die, and you're asking, out of this thing that you just did, where you flipped a coin and you rolled a die, what is the probability that the coin shows the coin shows heads and the die shows an even number? Or, not and. What is the probability that either the coin shows heads or the die shows an even number? All right, so if we go ahead and let's identify these, right? So all the events that have the coin showing heads are right there. Right, there's 6 of them. And so that's the head events. And all the ones that have an even number are here. All right. So if we count up the total number of things that just got circled, so evens are circled by purples, counting up the total number of things, for the head events, we had 1, 2, 3, 4, 5, 6. For the even events, we had 1, 2, 3, 4, 5, 6. However, these 3 were already circled because they're also head events. So we had 1, 2, 3 new ones. Right, so there are 6 plus 3, which is 9 events with heads or even. All right, the 9 events are, if you wanted to list them out, 1H through 6H, and then that's all the head ones, which includes 3 even heads as well. And then you've got 2T, 4T, 6T. Right, so the head events account for 6 of them, and then the 3 even tail events account for the other 3 that make up the 9 total events. Okay, so if you're asking what is the probability of this happening, we need to answer one question before that. In the problem statement, it was specified that this thing is a fair 6-sided die and a fair coin. And just remember what it means for things to be fair. Right, fair for a die and a coin means all outcomes are equally likely. All right, they're unbiased coins and dice, meaning that all the outcomes are equally likely. Right, so you're just as likely to get a heads as you are a tails. You're just as likely to get a 1 as you are a 4 or a 6 or whatever. Okay, so what that means is that if all outcomes are equally likely, then this tells us that every single outcome in this sample space where we do a coin and a die together, every single outcome there is also equally likely. All right, and this just comes from the fact that each of the two components in the experiment, the coin and the die, are both fair. All right, so all 12 of these outcomes in our sample space are equally likely. All right, so fair coin and die means that all 12 events in our sample space are equally likely. All right, notice that this is a slightly different thing than we saw in the last video, where we considered rolling two fair dice together and then taking the sum of what they showed and figuring out the probabilities of the different sums. That was different. That was fundamentally different than what we're doing now, because we had to do counting stuff, right? We counted up all the different ways that you could get a sum of 5 and a sum of 6 and a sum of 7, and there were different numbers of ways that this could be done. If you look at this sample space, you can ask the same question, right? How many ways are there of getting, for example, 3t? Right? How many different ways are there of getting that? There's precisely one way that this can happen. The die has to show a 3, and the coin has to show a t. There's only one way of getting every single one of these, which is why we don't have the same issue of two fair components being combined to give biased results like we did in the last one. All right, there's only one way of getting every one of these events, right? There's a very specific recipe that has to be followed. To get 3t, you have to roll a 3 on the die, you have to flip a tails on the coin. There's no other way to do it. Whereas in the last video, if you wanted to roll a 5 from 2 dice, you could roll a 1 and a 4 and a 1, a 2 and a 3, or a 3 and a 2. Right? There were 4 different ways that could have happened. So that's why here we've got a fair coin and die together, mixing together to give us equally likely 12 events, right? Because there's only one way that every one of those events can happen. Has to be whatever on the coin, has to be whatever on the die. Okay, so maybe I'm belaboring that point a little too much, but hopefully that makes sense. So all 12 events in our sample space are equally likely, meaning that the probability of any one of them is going to be 1 out of 12. All right? That's what equally likely means. You just take the number of events that you're looking at and divide it by the total number of events in the space, which is 12. All right, so the probability of heads or even. How many events were 12 or even? That was 9 events. And there are 12 total events. All right, so this is going to be 9 out of 12. That's 3/4. Right, 75%, if you like to think of it that way. Now, remember what we said near the very end of the last video. We saw 2 examples where calculating an or kind of probability, like this, the probability of this or that occurring, they broke down into a sum. All right, so if we look at the probability of H or even, what we saw last video was that it always ended up being a sum in that case. Right? Take the probability of heads plus the probability of even. Now, if we do this, let's think about the probability of flipping heads. All right, if we go up to our sample space, that's what's circled in red right here. Right, those are all the heads events. And there are 6 of them out of the 12 total possible events. All right, so the probability of flipping heads on the coin, this can happen in 6 out of 12 of the events. All right, so in other words, it's a 1/2 probability. And this makes sense because we're still just asking a question about a fair coin, right? What's the probability of flipping heads on a fair coin? Well, it's 1/2. And so this is consistent with that, right? So that's a good thing. We're not getting something that we didn't expect. Probability of rolling an even number on the coin. Well, that would be, I'll draw boxes here. That would be right there, 2s, 4s, 6s. right? Regardless of the outcome on the coin, it has to be a 2, a 4, or a 6 to be even. And there are 1, 2, 3, 4, 5, 6 ways that that can happen. 6 events in our sample space. So this would also be 6 out of 12. So, just adding them together, right? This is what in math we would call the naive approach. Naive is very often used as an insult in the English language, or sort of a demeaning term, derogatory term. This is not a derogatory term in math. In math, we call things naive approaches, meaning it's just the first thing that you think of. All right, so the first thing that we think of, because it worked in the last 2 examples we did in the last video, is just to add them together and see what we get. All right, so our naive approach, which is not a bad thing, it's just the first thing we're doing, says that if we add these together, we would get 6/12 plus 6/12, in other words, 1/2 plus 1/2, and that would tell us that we have probability 1. So simply adding them together tells us that you will always have something that shows heads or an even number, because probability 1 means 100%, right? This is a 100% certainty that if you flip a coin and roll a die together, you will get a heads or an even. That's what just adding them together says. But we know that that's false, right? Look back at the sample space. What happens if you, let me grab one of the events here that doesn't match that description. 1t. That's an odd number on the die, and that's a tails on the coin. That is not heads or even. It's neither, right? It's odd and tails. So this orange event here is an example of an event, and so is 3t and so is 5t. They're examples of events that do not match the description, right? They're not heads or even. They are odd and tails. All right, so we know that this cannot be true, right? The probability cannot be 1 because we just saw that it absolutely has to be 9/12 because we calculated it out to be that. All right, so what went wrong here, right? This is the question that we need to ask right now, right? So this, let me summarize this, right? Just adding them together, just adding probability of heads plus probability of evens is wrong. Number 1, why? And 2, how do we fix it? All right, so these are the questions we have to answer right now. Why is it wrong, number 1? And number 2, once we recognize why it's wrong, how do we fix it? So to try and answer this, I'm going to write our sample space again. All right, so if I write our sample space again, we have all of our head events. Oops, not 56. Doesn't make any sense. 5H, 6H. And then we have our tail events. And what we saw was that in figuring out how many events had heads in them, we looked at the row of heads here, right? So there are 6 of those. And then we looked at the events that have even numbers on the die. And that's these. So now, hopefully you can sort of see what went wrong here, right? If we just added together, like we did right up here in this calculation, if we just added together, 6/12 is the stuff in red, and 6 for the heads, and then 6/12 for the evens, that's the stuff in purple in this picture I just drew. Well, there's a problem there because there's overlap. Right? There is a non-trivial overlap between the event of flipping heads and the event of rolling evens in this probability experiment. In particular, these 3 events right here are the culprits. Those show the overlap. There's a 2 on the die, and there's heads on the coin. So it's both heads and even at the same time. This accounts for the error that we just got in this red calculation we just did that was wrong. All right, so how many events are there that have both? There's 1, 2, 3 of them. All right, so 3 events are both H and, not or, but and, even. All right, and if you look at how far off our answer was, right, this answer we got here that was wrong was 1. The actual answer, which we found just by counting up the events, was 9/12. How far off is 1 from 9/12? Well, it's off by 3/12. And look, we got 3 events that were in the overlap. 2H, 4H, and 6H were the overlap. Okay, so how do we, right, that's the why. There's the fact that there's an overlap there. And how do we fix it? Well, we now have sort of an idea. The bad answer we got is off by 3/12 from the actual answer. So this is how we go about fixing it. Right, so if we look at the probability of heads or evens, well, our naive approach said do probability of heads plus probability of evens, and this gave us the wrong answer. But it was wrong by this much. It was off by the probability of the overlap. So if we were to take that and subtract probability of H and evens, right, so that's the overlap, then we would have, right, this calculation we just did on the last page was 1. This is 3/12. Subtracting them gives us 1 minus 3/12, which is precisely 9/12, which is what we know the right answer is because we counted it, and we saw that that had to be the right answer. All right, so this is your general fact. All right, so your general fact here is right there. Probability of A or B is the probability of A plus the probability of B minus the probability of the overlap. Okay, I can draw a picture for this. All right, so let me use a Venn diagram. This is a very common way of representing, of visualizing probabilities. All right, so there's the probability of A. Or rather, there's event A, and here's event B. And let's say they have some non-trivial overlap, right? They overlap a little bit right there. Well, if I think about the probability of A, I'm going to visualize that as, let me actually use a different color. I'm going to visualize that as the area of this circle that I just drew. All right, so this area here is how I'm going to visualize the probability of A. Right, whatever the area of that circle is, that's what I'm going to say the probability of A is. And similarly, I'll use red. I'm going to visualize the probability of B as being the area of this circle that I drew here. All right, so if I'm asking, what is the probability of A or B? Right, this is the question. Well, then what I'm really saying is, right, if I just, grab any point, right, if I just sort of just draw a random point, right, so there would be a point right there. That point is in A, and so it satisfies the property of A or B because it's in A. Right, if I draw a point in B, that satisfies the property of being in B, meaning it's in A or it's in B because it's in B. And of course, anything in the overlap is in A or B because it happens to be in both, right? So it's in one or the other. And right, anything out here, right? If I draw a random point out in the middle of nowhere, that is not in A or B, so this would not be included in our calculation here, right? So if I'm trying to visualize the area of what accounts for A or B, it would be the following, right? So let me try to recreate this as best as I can. Right, so this here would be A or B. All right, it's just whatever the area of this, sort of like melting these two circles together and looking at the total area. This should be the area here. And if you try to think about how you could figure out this area, this purple area, from the blue area and the red area combined, well, you could say that, you add them together. Right, so it would be this plus the red area should give you purple. However, this is not exactly true. And if you look here, it's because the blue area, right, if I draw it like totally separately here, the blue area is this. The red area is also a full circle. And there's an amount here in the middle that if we simply added them together would be double counted. That red area in the middle would be double counted in this addition right here. Right, so this green area is double counted. And if that green area is double counted, well, to fix this this sum giving us the right answer, or giving us the wrong answer rather, to make it give us the right answer, we should subtract the amount that was double covered. And this green area in the middle here is exactly the stuff that's in both A and B. All right, so this purple area, which is what we want, is going to be exactly the probability of A plus the probability of B minus this overlap, which gets double counted by simply adding the areas of A and B together. All right, so we're in just adding those two probabilities together, we would be, if you visualize them as these areas, we would be double counting this this green area in the middle would be accounted for in both. If I draw it, whoops, that's the wrong color. If I draw it in this little picture here, right, it would be counted right there. And in this picture, it would be double counted right there. And of course, we only need to count it once. So that means that you should subtract it off at the end. All right, so this is the idea. We can do maybe one quick example, just to hopefully tie this together. All right, so another example here. What's the probability? Let's look at a 52 card deck. What's the probability of hearts or ace? All right, so let's say you draw one card from the deck. You look at that card. What's the probability that it's a heart or it's an ace? All right, so the gist of this is that using our formula, you would look at the probability of hearts plus the probability of an ace. And now you have to be careful and say, what if I happen to draw the ace of hearts? I should subtract off the probability that I drew the ace of hearts itself. All right, so probability of hearts, well, there are 13 hearts out of 52 cards. Probability of an ace, there's 4 aces in the deck. So that's 4 out of 52. And how many aces of hearts are there? Well, there's precisely 1 out of 52. Right, exactly one card in the deck is the ace of hearts. So this would be 4 out of 52 plus 13 out of 52 would be 17 out of 52. Minus 1 would be 16 out of 52. All right, and the idea here, right, if you were to actually count these out, there are 13 hearts and there are 4 aces. But one of those is the ace of hearts, so you would not count the ace of hearts, and you would just count the other 3 aces, ace of spades, clubs, and diamonds. That gives you 13 plus 3, which is 16 out of 52.